Hello, everyone. In this lecture, we are going to discuss generalized Markov models. So this is the outline of the lecture. In this lecture, we're going to focus on the renewal process. And in the next few lectures, we're going to talk about the renewal reward processes and the semi-Markov processes, as well as steady state and long-term analysis of generalized Markov models. So first, let's have a look at the DTMC, CTMC, and generalized Markov models. What are the difference? First, discrete time Markov chain is a discrete time stochastic process. You see here, this is indexed by n, okay? And the Markov property at each discrete time point, n equals to 0, 1, 2, 3, and so on. So this is deterministic and equally spaced, okay, discrete time points. The future of the system from any time n onward depends on its history up to time n only through the state of the system at time n. Okay, so this is a discrete time stochastic process at discrete time points. CTMC is a continuous time Markov chain. It's a continuous time stochastic process. You see here, this is indexed by t, and t greater than or equals to 0. So Markov property is at all times t, okay, greater than or equals to 0. The future of the system from any time t onward depends on its history up to time t only through the state of the system at time t, okay? So generalized Markov models, it's generalized. It's continuous time stochastic process. You see here, it is also indexed by time t greater than or equals to 0. But here, the Markov property is a set of possibly random time points. So here, the random is exponential. CTMC, the random distribution is exponential, but generalized Markov model, this random can be other random distributions, not necessary to be exponential. So those time points S0 equals to 0 and less than S1, S2, S3, and so on. So the future of the system from time Sn onward depends on the history of the system up to time Sn, only while the state of the system at times Sn. Okay, so main difference. This one is discrete time points, and they are equally spaced 0, 1. And at each time, you have a transition probability to all other states. And here, continuous time Markov chain is indexed by t, and the inter-arrival or the waiting time at a particular state, holding time, sojourn time is exponential. But here, the sojourn time is a general random distribution. Now let's have a look at the renewal process. So renewal process this is a random variable, nt, t greater than or equal to 0. It's a renewal process. If tn is a sequence of non-negative IID random variables, okay? So nt, obviously, this is nt. Nt is the count, okay? Nt is a counting process generated by Tn n greater than or equals to 1. Nt is the total number of events observed during 0 and t by time t. Okay. So let's have a look at this figure. You will have a better idea. So x-axis is time. So over time, you see this is the first event. So you have one event. So Sn is the time when the nth event occurs, Sn less than or equal to Sn plus 1. So this is S1, S2, S3. So S0 equals to 0. This T1 is the inter-event time between first one, the 0 and 1, the first event. And this is between the first event and second event. This is inter-arrival, or you can call it inter-event time. So Tn, for example, T2 equals to S2 minus S1. And in general, the inter-event time is equals to Sn minus Sn minus 1. Okay, so here we have a few random variables. So S is the time when the nth event occurs. And T is the inter-event time. And NT is the total number of events. For example, at this time, you will count total number of events observed up to time T. Okay, so NT is the counting process. That is how many events, the number of events generated by the random time, inter-event time, Tn. So here, Tn is a sequence of non-negative IID random variables, okay? So Tn is a random variable. So Sn is also a random variable, and Nt is also a random variable. And Nt will become a renewal process if Tn is a sequence of non-negative IID random variables. You see here, renewal process is Nt, and it's a renewal process. It's also a counting process, the number of events, but it's determined by Tn. Tn is a sequence of non-negative IID random variables defining the inter-event time. So if we look at a Poisson process, okay, and with rate lambda, which is also a renewal process, okay, Tn, the inter-event time is actually inter-arrival time is IID exponential lambda random variables, so exponentially distributed. But this for the renewal process, it does not have to be exponential. This can be a general or non-negative IID random variable, for example, uniform or the normal distribution. Okay. Okay. Now, the distribution. Obviously, we have NT as a renewal process. We are interested at the distribution of NT. So NT is the total number of events by time T. Sn is the time of the nth event. Okay, so Nt equals to max n, Sn less than by time T, and the nth event has to happen already, and the maximum one will become Nt. Okay. But because this Sn is a random variable, so Nt is also a random variable. So Nt greater than or equals to n if and only if the nth event occur before or at time t. So Nt greater than or equals to n, and Sn, this is equivalent to Sn less than or equal to t. So again, Tn is the inter-event time. If Tn follows this cumulative density function or distribution function, f, this is capital F. The Sn equals T1, T2, you add all of them together to Tn. So Sn, if Sn has a CDF function like Fn, okay? So if you recall the transformation of distribution that we discussed before in the previous lectures, so we have one random variable, right, Tn, and then we have the summation of n random variable. We talk about if we sum all the random variable together, it will be the convolution of all the n random variables. So if we sum them together, this CDF function is actually the n-fold convolution of the CDF for each random variable with itself. So we just do the convolution for this f n times. Okay. So now let's define the renewal function. Renewal function is actually the expectation of NT. So the NT is the number of events by time t. So this is the expectation. So inter-arrival distribution is F. Renewal function is MT. So MT equals to expectation of NT, which is also equivalent to the summation n equals to 1 to infinity probability Sn less than or equals to t. Okay, so by time t, if S1 less than t, by time t, if, for example, if there are already 10 events, so S1 less than t, then this is 1. S2 less than t is 1. You add all of them together, you will get the expectation. So because this is, what is this? This is a CDF function because less than or equals to. So you just add all the f and t together. Okay. So because you add all of the f and t together, this is, but each fn, for example, f10 is a convolution, 10-fold convolution. F9 is a 9-fold convolution. F1 is just the f itself. F2 is 2-fold convolution. So you need to add F1, F2, F3. So to infinity. So Fn is n-fold convolution, convolution of f itself. Okay. So now this equation is very important because it will later we will need this equation to derive MT. So suppose the first event occurs at a time x less than t. So suppose the first event occurs at time x less than t. So MT equals to expectation NT. This is 0 to infinity. If we write it as a conditional distribution T1, the first event when it happens equals to x, then we times the density function and dx. This will be the expectation. But given the first event already happened at time x, right? At time x. So we have one event already happened. Then we just add nt minus x because the first event happened at time x. The rest of the time is t minus x. So we still have expectation nt minus x. Then fx dx. If we put this into this parenthesis, we will get ft 0 to t mt minus x fx dx. Okay, so this is a convolution of m, and versus the fx. Fx is the PDF of the first event. Okay, and also the CDF of the first event. This is called the renewal equation. Okay, now let's have a look at an example. Suppose look at an example how to calculate the distribution of NT. So T1, T2, Tn, they are all exponentially distributed with lambda. So we know Ft is 1 minus exponential lambda. This is exponential distribution. This is a CDF function of the exponential distribution. So if we sum all sum of n independent exponential distribution. So we do the derivation before. If we add n independent exponential distribution, random variable together, it will become gamma distribution. So Sn is gamma distribution with parameter how many sum together add n exponential random variable. So this is n. The rate of each exponential distribution is lambda. So we put lambda here. So gamma distribution, when n is integer, it will become a long distribution. And if we recall the lecture before, we talk about the Poisson process. We talk about the Along distribution before. This is a summation of n independent exponential distribution. But gamma is very general. The n does not have to be integer. For gamma distribution, if n is integer, it will become a long distribution. So this gamma distribution, the Fn, is actually the n-fold convolution of f itself with itself. And because this is a long, so we know, and also gamma in general, PDF function is fsnt equals to, you see here, this is n minus 1 event, and then you have one more event at time t. Okay, and this is pt equals n. This is a Poisson distribution. So here we got the, we had a look at the distribution of NT, and also we revisited the convolution and how to use convolution to derive the summation of n independent exponential random variables. Now, I have included some MATLAB codes to do the n-fold convolution of CDF with itself, and also derive the MT and also renewal rate. Renewal rate is MT over DT. So in this example, let's first have a look at the density of inter-arrival distribution. This is an inter-arrival distribution, which is a uniform from 2.5 to 3.5. So the mean is 3. So this is Tn. Tn is PDF F, and the CDF cumulative density function is capital F. So we can get this. This is a PDF, the PDF function, probability density function, mass function. And we have, for the first inter-arrival, you see here, this is 3, and then random distribution between 2.5 and 3.5. And then once the first arrive, and then we generate a second uniform random variable, third random variable. So this is 40 independent realization of time of the renewers. So you see here in the very beginning, this is a uniform. And this is a 2 uniform distribution, 3 uniform distribution, random variable, you add all of them together, you see all the random arrive or renewers. So if we generate 4,000, this is a 14, because I couldn't really visualize 4,000 here. But in the experiment, I generated 4,000 independent realization of the time of renewers. You will be able to see the histogram of those renewal times. And if you add all of them together and at particular time, how many renewers you have, okay? And this is renewal derivatives of renewal function. We can go back. This is a renewal function. Renewal function equals to summation Fn. So F1 is just F. F2 is 2F convolution. F3 is the 3 F convolution, 3 CDF convolution. You add all of them together. So as you can see here, this is renewal 1, renewal 2, renewal 3. You also add all of them together. So based on the renewal function, we can derive the renewal function based on this equation. If you check the MATLAB function for this demo, you will be able to see I used this equation to derive MT. So once I derive MT, I did the derivatives. I will be able to get the derivatives of renewal function. Okay, so this is dm over dt. So we can see this is a discrete version. This is a continuous version based on the analytical derivation. They very well match each other, renewal rate. Okay, renewal rate means at a particular time interval, how many renewals you may have, the rate of the renewal at a particular time interval. So density, now we change the density to be normal distribution, normal random variable. So mean is 6.997. So here, you see this is a normal distribution. This is a second normal distribution, right? You have the first normal random variable, then you add the normal random variable again. And so this will be the summation of 3 random variables. Okay, this is the summation of 4 random variables. Okay, so you can see we also got the histogram, and we got the renewal rate, and based on the analytical derivation of the renewal rate function. And I also simulated the exponential and the random variable. So you see exponential, you got a constant renewal rate. Okay, constant renewal rate. Now let's have a look at a battery replacement example. Suppose Tn is the inter-replacement times. We're going to replace a battery as soon as it dies. So NT is a number of batteries replaced during the first T years of car life. Ln is the lifetime of the nth battery. And now we're going to replace the battery as soon as it dies. So Tn will equal to Ln because we replace the battery when it dies. Renewal process if Ln is a IID non-negative random variables. So we replace, this is the first policy. We replace battery upon failure. The second policy is we replace the battery once it becomes 3 years old. So this one obviously is a renewal process. And the second policy, our main objective is to reduce unscheduled, unplanned replacement. So whenever it becomes 3 years old, we replace it. So NT is the number of battery replaced up to time t, planned or unplanned. So T1 is the minimum L1 3. That means if the lifetime, if the failure is before 3, this is unplanned, okay? So the first replace time is at 3, and if it's not failed yet, we're just gonna replace it as 3. Or L1, the lifetime. If lifetime, the first lifetime of the first battery is less than 3, we're gonna replace it before 3. If L1 greater than 3, we just replace that at time 3. The same for all the second inter-event time and the third nth inter-event time. Obviously, the lifetime is IID non-negative random variable. So Tn is minimum Ln3. So it's also IID non-negative random variable. So NT is also a renewal process. So under both policy, this NT is a renewal process. Now let's have a look at the long run renewal rate. So the long run renewal rate Tn is the IID non-negative random variable with common mean. Let's suppose it has a mean tau, and Sn equals to T1, T2, and because this is the nth event, so you have to add all the n inter-event time together, you got Sn. So long run, this limit n, when n goes to infinity, Sn divided by n equals to tau. So this is the nth event, and you divide by how many events you have. This is the average, okay, the mean inter-event time. So you can do the derivation with you can look at this in a intuition. So inter-event time, suppose the inter-event time just tau, deterministic. So at nth event, you have n tau, okay? So the nth event occurs at time n tau, so Sn over n equals to n tau over n equals to tau. So this hold even if Tn is an IID random variable when the limit n goes to infinity. Now let's have a look at, with this result, let's have a look at long-run renewal rate. Long-run renewal rate is NT over T. This is actually 1 over tau, okay? So this is a constant, just a 1 over tau, 1 over mean, okay? So this is long-run renewal rate. Let's prove this. Because we have this result, and we use T over NT. So this will become SNT, capital NT over NT. This will be SNT plus 1 over NT, okay? Obviously, this one actually equals to tau, and the right-hand side equals to limit. You just add 1 and also NT plus 1 over NT. So you see here, this one is tau, this one limits goes to 1, so this is tau. So left-hand side is tau, right-hand side is tau. So when t goes to infinity, this t over nt is actually equals to tau. So nt over t is 1 over tau. Okay. So if we go back to this result, you see here, the tau, we know the tau inter-arrival time mean. So when t goes to infinity, the renewal rate should goes to, the renewal rate will go to the constant 1 over tau. You see here, this is actually when it go beyond, this is actually 1 over 3.3333 over here. If you look at this, this is also 1 over approximately 7, 1 over 7. If you go simulate it long enough, it will goes to the constant. And obviously this one is constant, right? 1/1.4. Now, let's have a look at an example. For the Poisson process, NT equals to Poisson process lambda. So this is a count. And Tn is exponential. Inter-event time is exponential. So the mean is actually tau equals to 1/lambda. So mean this long run renewal rate equals to lambda. It's just lambda. Okay. So if we look at it from the Poisson process, Poisson distribution point, this expectation NT for this Poisson, and you see this is lambda t over t. So this will equals to lambda. So the expected number of event per unit time is tau. If you look at this exponential, right? This is the interarrival. This is actually a Poisson process, and then we can have this mean is actually 1/lambda. So lambda actually, so mean, let's have a look at this mean. This t exponential mean is actually 1/lambda. So the expected number of event per unit time is lambda. So if we got this 1/lambda equals to 1.4, so this is actually 1/1.4. Okay, now let's revisit the battery replacement example. If we replace the battery on pump failure, suppose the inter-event time is uniform between 1 and 5 years. So the mean is actually 1 plus 5 divided by 2 equals to 3. This is uniformly distributed lifetime. Okay. So because we have this mean equals to 3, so the long run renewal rate is NT over T, 1/tau, 1/3. So the rate of replacement is 0.333 per year. Okay. So under the replacement on pump failure, the rate of replacement is 0.333. What about replacement at when it becomes 3 years old or on pump failure? So this is a new policy, mean LN3. Let's look at the rate of replacement in this new policy. So if the replacement policy is the minimum LN lifetime and 3, so tau equals to expectation. Let's first calculate the mean. So this mean is actually minimal LN3. So if it is between 1 and 3, this will be X, the lifetime. So this is X 1/4 because this is uniform distribution. And if it is more than 3 and 3 to 5, then this is 1/3. This is 1/4 because this is 1/5, right? So this is 1/4. 1 and 5. So this interval length is 4, 5 minus 1. So between 1 and 3, you have X 1/4. And we're going to replace just at 3. And so if the lifetime is from 3 to 5, so this is 3 times 1/4 dx. So with this, we can calculate the mean is about 2.5, but previously the mean is 3. So the rate of replacement will becomes 1/2.5. This is 0.4. It's much higher than 0.33. That means that we replace it faster. It's higher rate. Why we want to replace that higher rate? Because we want to avoid or reduce the unplanned replacement. So we want to avoid some troubles, because on pump failure, we're going to have some troubles, right? So we couldn't, if the battery is failed, then we couldn't go to work. We have some other cost associated with the failure of the battery. So at a higher rate, we actually avoid some of the unplanned maintenance. Okay. Now, what is the rate of the unplanned replacement up to time t? That NT to be the number of unplanned replacements up to time t. So T1 is the time of the first unplanned replacement. So if L less than 3, the first placement, is unplanned. Okay, T1 equals to L1. If L1 greater than 3, the first placement is actually planned. So the take place at time 3 and the expect time to the unplanned placement is still tau. Okay, you see here, when L1 greater than 3, then the first replacement is not unplanned, it's planned. So it happens at time 3. Then after time 3, you continue to go move forward, and you have already replaced, right? Then if the next one is unplanned, then the expect time is still tau, and from then on. So L1 is uniform 1, 5. So if tau equals to expectation T1, this is unplanned. So if L1 is less than 3, and this will be probability L1 less than 3, and the T1, this is our unplanned, right? If L1 greater than 3, you have to you have probability, this is 3, expectation 3, and then you have to add tau again. Okay, this is a conditional expectation. Actually, in the previous lecture, we talked about condition on the first one is unplanned, and then you got the expectation, and the condition on the first one is planned, and then you continue to go forward. This is still tau to the next unplanned. Okay, so this is 3 plus tau probability L1 greater than 3. So this will become 2.5 because this is actually the expectation minimum L1 3. Okay, L1 3. So this is 2.5 plus 0.5 tau, and we solve for tau equals to 5. So the unplanned replacement occur at a rate 1/5 equals to 0.2, which is much less than 1/3. 1/3, what is 1/3? Replace upon failure, okay? Or 1/2.5. And no matter it's what 2.5 is, no matter it's planned or unplanned, and this is average. So the unplanned replacement occur at a rate is much lower. Okay, so far we talk about the MT, the renewal function, and the renewal rate, and the long-run renewal rate. Now we talk about the expectation of NT, because NT is a counting process, total number of events by time t. So NT has expectation. We talk about how to calculate the expectation. It's n-fold convolution, and F1, F2, F3, and you add all of them together. Now, we also want to know what is the variance of NT, okay? So by this asymptotic distribution, we are trying to see what is the distribution of NT, okay, by central limit theorem. So let's recall that NT greater than or equals to N if and only if the nth event occur before or at time t. That means NT greater than or equals to N is actually nth event occur before or at time t. So NT less than N is actually, so if by time t we don't have n event, then Sn should be greater than t. Okay, so those are equivalent. So Sn is the nth event. Nth event equals to the sum of the inter event, like the first event, second event to the nth event. We know that for each t inter event time, is a random variable with mean tau variance sigma square. So when the st goes to infinity, we know that Sn greater than t equals to nt less than n. Because the nth event happened after t, it means the nt, we don't have a total number of n events before time t. So this statement is actually equivalent. So by central limit theorem, because this is a summation of n random variables, each one of them is distributed with mean tau and the variance sigma square. So the central limit theorem tells us the Sn is approximately distributed, normally distributed with n tau and the n sigma variance n sigma. So the standard deviation is square root. And if we do the standardization, so Sn minus its mean divided by the standard deviation, it will become standard normal random variable, that is z, denoted by z. So Sn greater than t will become z greater than t minus n tau over the square root of n sigma square, because Sn is approximately normally distributed with n tau and the variance n sigma square. So if we write it as phi, because this is a normal random variable, standard normal random variable, phi z is actually, we can check the table to find the CDF function. And then this is upper percentile CDF function. So that means this is upper tail, not lower tail. And so this will become phi t, this value. And we also know this actually equals to p nt less than n. And nt, if we minus the expectation divided by the variance, this will less than n minus expectation nt divided by the variance nt. Okay, here, so this should be the standard deviation. This v actually stands for the standard deviation, because if we want to do the normalization or standardization, we subtract the mean divided by the standard deviation. So this is the standard deviation. So just like here, it should be a standard deviation. Okay, so z less than this value is actually should equals to this, because we know nt less than n equals to Sn greater than t. So this value, we put it right here. So this value. Now, what we really want is the expectation and the variance. Now let's continue to look at it. So we know this probability z less than n equal minus the expectation divided by the standard deviation, and this will equals to phi t minus n tau over n sigma square. So which equals to phi greater than z greater than t greater than this, right? T minus n tau divided by square root of n sigma square. We know phi, the normal distribution is symmetric. So that is phi z is actually equals to phi minus z. Okay, because z is standard normal, so it's symmetric on the 0. Okay, center at 0. So if we switch, okay, we use n tau minus t, this will be less than, but this one will be greater than. Okay, so n tau minus t, if we divide by tau, this will become n minus t over tau and n sigma square over tau square. So at this moment, we can derive that because n equals to tau t over tau as t goes to infinity, because t goes to infinity, and t over tau is actually n. So expectation nt, so this is the expectation of nt, because expectation nt greater than n, nt or less than n. So this is less than n, so this will be n minus t over tau. So this expectation nt is t over tau. Variance of nt is actually, because this is a standard deviation, right? And if we put it out, it should be t sigma square over tau cube. So this is approximately equals to n sigma square over tau square, because this is standard deviation and this is a variance. And so now we know that asymptotic distribution of the nt is actually mean, is expectation is t over tau, and because here this is t over tau equals to the n, expectation nt is actually n, right? So variance nt equals to approximately t sigma square over tau cube. So by the central limit theorem, and we can we can do the standardization. So we got the standard normal random variable. And for large T, NT is approximately normally distributed with this mean and this variance. So central limit theorem for renewal process, the variance of NT when T goes to infinity divided by T equals to sigma square over tau cube. Okay, so the main results, asymptotic distribution, main results is expectation NT is approximately T over tau. And the variance of NT is approximately T sigma square over tau cube. So this is the main results of the asymptotic distribution. Now let's have a look at an example of how to use this asymptotic distribution. Suppose we have two machines. They continually process an unending number of jobs. So machine one is actually T, this is 1, the inter-arrival time is gamma for 2. So the gamma distribution for 2, the mean is 2 and the variance is 1. And this is uniform, the mean is 2, variance is 16 divided by 12. So N1T is the number of jobs processed by time T, and N2T is the number of jobs processed by time T and also by machine 2. This is by machine 1. So find the probability that two machines can process at least 90 jobs by time T equals to 100. Okay. So this is NT, T equals to 100. So now let's have a look at N1. So by machine N1T, N1 100. So by machine 1 by time 100. And this is normally distributed with actually with T over tau. So T over mean is 2. So 100 divided by 2 is 50. And then variance is T 100 times 1 divided by tau cube. Tau cube is 8. So 100 times 1 divided by sigma square divided by tau cube, this tau. So 2 power 3 is 8. So number of jobs processed by machine 1 by time 100 is this is the distribution. And by machine 2, similarly, is normally distributed by 100 T over tau. So 100 divided by 2 is 50. And then the variance is T sigma square 100 times 16 over 12 and divided by 8. Then with a little bit derivation, you can get 100 by 6. If we add these two normal random variables together, we got the two machines can process by time T equals to 100. So N1 100 plus N2 100 is approximately normally distributed. We add these two mean together, add these two variance together. So 50 plus 50, 100. 100 over 8 plus 100 over 6, this is 175 over 6. So the probability can process at least 90 jobs by both machines. So by combining the both machines, so this variable greater than 80, at least 90 jobs. So it should be greater than 89.5. And that's just because this is discrete random variables, right? So we just calculated greater than 89.5. So this equals to Z greater than 89 minus 100 divided by square root of this. Okay, this is equals to 10.5. 89 minus 100. So this equals to 1.944. So this is actually the greater than 89. So this equals to 0.975, 0.9741. Okay. So anyway, if we check the distribution, this is our distribution. Okay, check the standard normal random variable. This is in a probability theory. Then this will equals to 0.9741. Okay, now this is the end of our first lecture on the renewal process. And in the next lecture, we're going to talk about renewal reward process and semi-Markov process.